Hi, my name is Pablo Barros, and I'm here to give you a short introduction and summary of our most recently published paper, which has the huge name of Adapting the Interplay between Personalized and Generalized Affective Recognition based on an Unsupervised Neural Framework. This paper was published by the Transactions on Affective Computing and is available online right now. Well, recognizing affect is not a single task, as is led to believe by the wave of recent research and papers and models on affective recognition, mostly due to the advance of deep neural networks, recent advance of deep neural networks. Most of this work based on the fact that you can extract specific features which are general enough to carry some sort of general affective concept with them, and then associate these features with labels. The problem is when you try to adapt and use these models on real-world scenarios, they do not adapt easily to the concept of personalization. Every person has their own specific way of expressing emotions. This is not captured by the general aspects of these features that are learned by these models, but by interacting with this person over time, we can observe and we can assimilate these specific characteristics to identify how that person is expressing emotions in a particular way. This is usually not adapted to these deep neural network models, and this is a problem that we try to address in this work. The main challenge when addressing this problem are twofold. How to maintain performance of these models, this great generalized performance, while achieving an online learning that is able to adapt to specific individual characteristics of a person with very few data points. We address these problems by proposing and formalizing the affective memory framework. This framework is composed of modules that will address specific problems of affective representation in a general and personalized way. The first part of our module is how to represent multimodal affect, and we propose a deep neural network that represents audio and visual features into affective information. The second part of this framework uses these features recognized by the first module to create clusters of non-affective representations. These non-affective representations are then used to generate a general knowledge of what is being perceived by the network. In parallel, the affective representations are used to train in an online manner specific affective memories that will map the specific features of that specific person with known concepts. This way we can have a feature map of how that person expressed that specific emotions. Finally, the last module of our network will combine the personalized and generalized affective representation of that person into one single affective state. This network is a stateful network that will create specific readings in terms of arousal and valence, defining the affective state of the person. Our first module is composed of a cross-channel convolutional neural network, which is a topology we previously proposed for recognizing affect from audio and visual features. This network learns how to represent affect in a supervised way and extract affective features from face and audio and combine them into one single representation. This representation is fed in our second module to a growing and required network. This unsupervised network creates prototype neurons that represent perceived stimuli. That means that the network creates clusters of neurons inside its stateful representation that approximate perceived features. By pre-training this network with a large amount of data containing a general view of affect from different persons, we are able to to create and identify clusters inside the network that represent general known concepts of emotions. At the same time, we have in parallel the third module running, which creates specific growing and required networks, individual networks for every person the network interacts with. These networks are updated only when only when the stimuli from that person is received by the network. These networks will contain the same idea of affective clusters, but now for that specific person. That means that it will create prototype neurons that will represent the affective representation of that specific person within one network map. These two network maps are fed to a third growing required network that will combine the personalized and generalized readings into one single reading. Each neuron on our last layer, which we call mood, have one neuron that represents one arousal and valence perceived from that person in particular. By tracking the formation and the deletion of these neurons over the network over time, we have a temporal representation of affect that was perceived by the network from that specific person. To evaluate our performance of our model, we need a different data set, a different data structure to show that this evolution of personalized and generalized affect happens within our model. For that, we use the OMG emotion dataset. This dataset contains more than 500 videos of monologues, which are ideal to demonstrate how the single person expresses emotions in a varying way over a long period of time. Each of these videos contain one individual person, and we are able to recognize and evaluate our model in terms of general affective recognition, but also personalized and individualized affective recognition. To better understand each module of our network and how it contributes to the final performance of our model, we propose an investigation of the performance of each module individually in terms of concordance correlation coefficient, which is the standard metric for the OMG emotion dataset. As we can see, and how we expected, each module contributes to the next one in terms of performance. By the end of our network, our last module, the mood module, we have the best performance of the whole framework. But the most interesting for us is not the raw performance, the pure performance of the model in terms of a metric, but it is how the model learns and adapts in an online manner to achieve this performance. For that, we did several types of different analysis and observation on how the different parameters of the model and how different modules of the whole framework behave when fed with the monologue data from the OMG emotion dataset. In this presentation, due to time, I will just show our final analysis on the individual modules of the generalization, personalization, and the mood modules. And we see that while the generalization model has a performance which is somehow continuous because it doesn't learn, it doesn't adapt, the affective memories, the personalization module, have a very different behavior. It learns online how to integrate these different features into emotional concepts, meaning that in the beginning of the video, only with a few seconds of information, the performance of this module is very low, but it grows over time. With the final integration module, which integrates the personalized and generalized representations, we can see that we have a hybrid behavior, which already has a good performance in the beginning, which we then address as a first impression effect. I kind of have an idea of this emotion, of what this emotion is, but I don't know what this means for that specific person. But this is good enough to have an impression, a first impression of this affective representation. Over time, this grows and this improves, reaching the best representation we have as an average of time-wise. This happens for both arousal and valence observation on the videos of the OMG dataset. And for us, this is the best way of display how our model actually learns in an online manner to adapt towards these specific characteristics and merge the concept of first impression to the concept of personalizing, of knowing someone over time. Well, in conclusion, we show with our paper that generalization personalization can be represented as a factor of feature recombination. The entire model is based and relies on a strong feature representation. Once this strong feature representation is done, the model is not retrained on this level. That's why the learning of the model can happen in an online manner in a very quick way. Online adaptation of affective features towards one single person was shown possible, and was shown that it improved in the end the general performance of the model towards affective recognition. Our last module provides a continual affective reading over long videos, averaging and aggregating these temporal aspects of affective reading over a long video. And of course, I would like to remind you that this presentation, this video, just contains a short discussion, a short analysis of our whole paper. If you want more information, the paper is freely available at the IEEE Explorer, and we have the model fully available with our experiments on a GitHub account, and both links you can find here in the end of the video. Thank you very much.